Hi, good evening, guys. I'll start at 5:45. Okay.
Okay, sir.
Okay, so if you remember last week we ended with this discussion on radian and steradian, and I also discussed why steradian concept of steradian is important here, because antenna will be radiating or receiving not only in a surface, it will be acting in a volume. you know so when the volume comes, we have to have a cone of action, right? So this cone, whenever we have a volume, then we have a cone, and this cone can be represented as steradian or solid angle, and this is described as d of omega, capital omega, given by sine theta d theta d phi. So you remember this thing, because later on in all the other calculation like directivity and gain and all this power intensity, we will need this. Okay. So the first topic of discussion today is radiation power density. Um, so it's a very vital concept, and because we deal with power here in high frequency, not with voltage or current, so we don't have a concept of what which is given in normal circuit theory as multiplied by voltage and current. Instead, we have a power density. So what that we get generally from multiplication or cross product of electric field and magnetic field. Right. So instead of voltage and current, we are dealing with here electric and magnetic fields in high frequency. So that's why we need to go to this power density concept. And it is also mentioned as a Poynting vector, right? So this Poynting vector or average power density is given as, it is half of the real part of E cross H prime. So why this but this E and H, these are all mainly it is the vectors without the time concept. Okay, so if you take out the time, we have the electric and magnetic fields, only the spatial content. So that is given by the average power density, and this the power density with this fields of antenna, these are all calculated in far field region. So the concept of radiation density or power density comes only in far field region. And if you take average power radiated by antenna, so that has to be taken, this is throughout the surface, because the power density is given, the unit is watt per meter square, because it's a density of power per unit surface area. So total power radiated over a surface, average power will be, you have to take whole surface in the vicinity of the antenna. So that if you take, it comes like half of the real part of E cross H star. Yeah, is this question clear? Is there any doubt on it?
No, sir.
Okay. Okay. So we are here from power density, we can calculate power radiated, average power radiated from this. Okay, next is radiation intensity. So this is mainly used over the power density. So there are two concepts. One is radiation density, another is radiation intensity. So radiation density was power radiated per unit area, and here it is defined as power radiated per unit solid angle. Okay, so that's the difference between radiation density and radiation intensity. And the definition goes like is capital U, and it's given by R square omega rad. So where omega rad is the radiation density. So and radiation intensity and radiation density, they have connected with in terms of R square. So yeah, if you see the definition, and so it all comes from the definition of this. Here. Here you see the capital omega is given by d omega by dA by r square, right? So this r square is taken into that angle. Because in one case, it will be P divided by d omega radiation intensity. And radiation density is P by dA. So really this r square term is going to connect both of them. I hope you understand what I'm saying. So that's why radiation intensity and radiation density is connected only in terms of r square. They have a relation r square. This comes from the previous definition of solid angle. Is it understood?
Yes, sir.
Okay. So the total radiated power, just in the same as the previous case, here also we have total radiated power given by U d omega. So where U is the total, this is the total radiation intensity, and d omega is the solid angle. And this you see is a bounded integral. Okay. So it's a bounded integral over some solid angle. And is given by, if you calculate, so really it comes in terms of d omega is sine theta d theta d phi. So which comes from this, the same equation again. D omega is given by sine theta d theta d phi. So this equation, as you see, is very vital. You must remember this one. So from this you can calculate total radiation power, radiated power. Yeah. So now the main concept in antenna, one of the main features of antenna is given as directivity. So what is it actually? IEEE defines it. So this is the IEEE definition of directivity of antenna. What is it said? The ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. So that's why in the equation here you see D equals U by U naught. So it's a ratio of radiation intensity in a particular direction. This U is the intensity in a particular direction, and 2 ratio 2 is radiation over all directions. That's given by U naught. Okay. So why this U naught is the radiation intensity averaged over all directions? That we'll see. The next line says the average radiation intensity is equal to the total power radiated by the antenna divided by 4 pi. So that is why in the next line, next equation, you see U naught is given as P rad divided by 4 pi. So that says that if you have a omnidirectional antenna, the power radiated will spread throughout the area, right? Not in any particular direction, but in all directions. So that's why then it will be averaged over P rad by 4 pi. Okay, so why this U naught is P rad by 4 pi? So there the radiation intensity is given by radiated power per solid angle. Okay, so now if it is radiated over all throughout the angles, the total solid angle is given by 4 pi. In a circle, the total solid angle you can get is given as here. Here if you see, if the antenna is situated in the center of a sphere, the total solid angle it will extend over the sphere is 4 pi. Okay. So you see it is written there 4 pi steradian in one sphere. So that's why this, the radiation intensity will be here U naught equals P rad divided by 4 pi. So I hope you understand. Here this equation P rad is given by U sine theta d theta d phi. If U is constant, if you take out of this integral U naught, then if you take integral of sine theta d theta d phi over 0 to pi 0 to 2 pi, it will come as 4 pi. So that's why it will be P rad will be U naught into 4 pi. So that's why the radiation intensity U naught will be P rad by 4 pi. That is what we are having here. So that is given as average radiation intensity in all directions. And that is used for the definition that is used to define the directivity of the antenna. Yeah, now is it understood? Is there any question? Did you understood how the definition is related to this equation?
Yes, sir.
Okay, okay. Yeah. So yeah, you tell me if there are any doubts or questions. Okay. Okay. So
So
this
this is
is
the condition of an isotropic or a omnidirectional?
it is yeah, it is
We-
isotropic. Right, right. Yeah.
Isotropic, yeah, okay.
Yeah, yes, yes. So then only we will have it uniformly spread in all directions. Yes.
Okay, sir.
So yeah, the next line says if the direction is not specified, then the direction of maximum radiation intensity is implied. Okay. So many of the times you will have directivity. So this directivity means uh, directivity in maximum radiation intensity. So in some direction you will have the radiation pattern will be maximum in some direction or some angle. So we generally mean that direction only when referring to a directivity. And the next line, the next equation shows D max is the maximum radiation intensity given by U max by U naught. So it's the same as previous equation only. So only that the direction of this U max is the radiation intensity in the maximum direction. So you have to have that angle and calculate it accordingly. It's nothing else. So yeah, I suggest you look into this portion of Balani's book. So there are one or two solved examples there. So if you go through that, it will be very much clear. And the next thing is directivity, how it is calculated. So often it is also written as 4 pi f theta phi maximum and given by averaged over f theta phi sin theta d theta d phi. So it comes from the previous equation, and this f theta phi is the radiation pattern given. Okay, it's the radiation pattern or the radiation intensity given in that term. If you further normalize this equation, it comes as the d naught equals 4 pi divided by this. So there you see in the denominator we have this f theta phi divided by f theta phi max, right? From the previous equation only it comes. If you take the numerator also in the denominator, then we have equation in a simpler form 4 pi divided by omega a, right? This omega is called beam solid angle. So this beam solid angle can be calculated from your radiation pattern, and that in turn can be used to calculate directivity. So see here you note that beam solid angle is calculated from the denominator. So this equation in the denominator, the integral form can be used. Now we have some simplification. In a radiation pattern, we have the concept of the half wave angle. Okay, so this means the angle what is used where the power will be half power of the maximum, right? So that if we have theta 1r and theta 2r in two perpendicular planes, in the left side picture if you note, there are theta 1r and theta 2 are noted. This is in two perpendicular planes. Then the beam solid angle can be simplified in terms of almost equivalent to multiplication of those theta 1 and theta 2. So that can be used to very simplify this directivity very much given by 4 pi by theta 1 theta 2. But you need to remember that this theta 1 theta 2 is given in terms of radian. So that's why it simplifies further in terms of degree, as if you take radian to degree conversion, it gives around 40,000 divided by theta 1 degree, theta 2 degree. So D means degree and R means radian. So that means if you have a radiation pattern, given radiation pattern, and you have your half power beam width also given, from that you can calculate directivity. Yeah, I hope this is clear.
Yes, sir.
Yes, sir.
Okay, so now I have a question for you. Why this theta 1 and theta 2 is taken in two perpendicular directions? Why not just some other theta 1, theta 2? Do you know any significance of that? So, yeah, tell Nandana. Yeah.
No, sir.
Yeah, so why this theta 1, theta 2 is there? Is there any particular significance? You know, if you have the antenna measurement things, we will have, how do we correlate with that? How do we have this theta 1, theta 2? Any idea?
No, sir. No, sir.
Okay.
I
Okay.
don't-
Yeah, just try to think why. So, you know, if we have an antenna and measure the radiation patterns, so how called?
So can you repeat? The voice got break.
I am saying if we have an antenna and if we measure the radiation pattern, what are the planes of data or the radiation pattern will be collected? In what planes?
E theta and H5. Is that?
No, not about theta and pi. They are called two planes where we collect the yeah. Binay?
Azimuth and elevation.
Azimuth and elevation, right? But we generally call them in terms of E plane and H plane.
Yes, sir. Yes.
If you remember, I will go back. I don't know how we forgot it so quickly. This last week only I discussed this. That's why it's relevant, important, right? It is very much important. But it's E plane and H plane. So all the antenna patterns will be generally measured. We cannot measure all 3D angles. In 3D, you can have many angles. We generally take two perpendicular plane patterns measurement. Okay, E plane and H plane, and they are perpendicular. Yeah. Do you remember this concept, E and H plane?
Yes,
Yes, sir.
Yeah.
Sir,
So because
but
yeah,
there is, but we can't say directly like theta theta 1 and theta 2, which is E and which is H.
yeah, that
Can
is
we
what
say
I'm
that?
saying. Yeah, if we have two perpendicular planes, because we have two perpendicular planes already in our measurement, we can take those as theta 1 and theta 2. We don't need to take care of any other
Okay,
angle.
in y direction at one point, theta 1 of one angle and theta 2 in perpendicular. That's
Yeah, right. So they
okay.
are like has to be perpendicular, and in this is in a picture or in a simulation you can easily draw it. But in antenna theory is practical. You have to fabricate antenna, measure it. So there you have only two planes, E plane and H plane. So from that you can calculate this theta 1 and theta 2 easily, and from that you can calculate directivity. Understood?
Yes, sir.
Okay. So now we will look into antenna efficiency. Okay. Yeah. So antenna efficiency is important. Okay, now I want to ask you only. So why do you think this term antenna efficiency is required? What was missing in previous equations? We talked about antenna directivity. So antenna is given some power, and whatever the power or power density in some other direction received, that we were discussing, right? So why this antenna efficiency is required?
Calculate the how much reflected power or wastage power.
Come again.
To calculate how much amount gets reflected, power gets reflected.
Okay.
Efficiency will
Yeah, reflection is one, and another things. What are other things?
gain.
No, gain does not come here. Gain will come later. Pavan, yeah, any idea? Pavan,
Like
yeah.
circuit element losses, like losses in the antenna.
Sorry, what circuit element? I did not understand.
Like if we consider as antenna as a resistance, and
Mhm.
if you are feeding
Yeah.
with a source, there should be some losses in the antenna,
Mhm.
which
Yeah,
radiates.
yes, you are having the point almost there. So the thing is like there will be losses in the antenna itself. So we have to take care of the losses. We will be feeding the antenna with some power. So how do we feed it power to antenna? Through a transmission line. So there will be a junction between the transmission line and antenna. So this will cause a reflection coefficient mismatch or matching. So matching will not be exact. So because of that, there will be some power reflected. Further, in the antenna itself, we will have dielectric loss as well as metallic loss. Okay, so that is what it says here. There will be losses occurring in the antenna due to reflections that happens because of mismatch between the transmission line and the antenna. So I hope that you understand that there both these two different components are already present in antenna. One is transmission line, another is antenna itself. Transmission line used to feed the antenna, and the second loss is I square R loss. So which comes from just like the circuit theory, it comes from conductors and dielectric. So we have to take care of all these things because when we say about directivity and all these things, we receive at some point in far field. First, we have to take how much power is actually getting transmitted. So there are all these losses you have to take care of. That's yeah. So now the definition says overall efficiency is given by E naught equals ER, EC, and ED. Okay. Yeah. Anything, Nandana?
No, sir.
Okay. So this EC and ED is taken as same as one component. So it is conduction and dielectric efficiency together, and the reflective loss, as you know, is given as defined as one minus gamma square, because that's the uh, ratio of the input power to the reflected power. Okay. So reflected power, if you give some power, gamma square will be the reflected power, and that's why 1 minus gamma square is the actual power accepted by the antenna. So, and that's why it's given as reflection efficiency 1 minus gamma square. Is that understood?
Yes.
Okay.
Yes.
Now we will build upon our definition of directivity and efficiency to have a definition of antenna gain. Okay, so the concept in the what happened in directivity is that we are only talking about some power we received and some power something happened in the how much power is there in the some far field region, but it does not actually take care of the directivity does not take care of input power. That is what we have to take care here now. That's why the gain concept was there. Yeah, give me a minute. Okay, so here what we are doing additional to directivity is that we are taking account how much power the antenna accepted. Okay, not about just some power of antenna. We are taking care of at the terminal of antenna how much power was accepted. Okay, so you see here the definition says gain equals 4 pi into radiation intensity divided by total input power. Total input power, that means total accepted power in the antenna terminals. And now should we go to the other one? Let's see in the directivity what did we have. Here we have P rad. That means P rad is radiated power. So it was saying how much power was radiated by the antenna, right? But it did not actually talk about how much power the antenna received. And then some losses occurred and then radiated, right? So that's why the gain is even a more solid concept or more powerful concept than directivity. It talks about the input power. So when you talks about now how is the radiated power input power is related, here you see it says P rad equals ECD in multiplied by P in. That means some power now you see the picture in the left side. In the input terminals, it is the gain reference. But gain, antenna gain, we have to refer to the input terminal in the left side. And for the directivity, we are referring to the output terminal of the antenna. So what power was radiated from the right hand side. And the left hand side, it sees how much power is input. And in the antenna, we have the losses due to conductive and dielectric losses. So that's why P rad is ECD multiplied by P in. Okay. And the further we have GCD equals given by 4 pi. And if you put these values in the previous equation, we have the relation between directivity and gain. It is also related with a coefficient of multiplication ECD. As you should know that ECD is less than 1 always because it's losses, right? It will be always less than 1. If no losses are occurring, ideal case, we will have 100% efficiency and ECD will be 1. And generally it will be less than ECD. That's why gain will be always less than directivity. Is this part clear?
Sir, but that IEEE standard definition is showing it does not include losses arising.
Yeah. Losses arising from no. So you see, they are not talking about the antenna losses. IEEE standard says gain does not. That I will coming to there. So we have now multiple definitions of IEEE gain of gain. That I'm coming. But so far, is it clear what I said?
Yes, sir, yes.
Yes,
So
but
Sir,
yeah.
can you explain this P rad is equal to efficiency of conductance and conduction and dielectric into power?
Oh, okay. So see, input power is the power accepted by antenna in the left hand side of the picture, right? You see the gain reference force portion is written in parenthesis. Do you see that?
Yes.
Yeah. So in there we have P in. P in is the incoming power to the antenna. Now in antenna, what happens? Here we have, see the IC, ID, all this that causes the loss ECD. ECD is the loss happening in the antenna itself, conductive and dielectric loss. Understood?
Yes, sir.
Yeah. So obviously in the other output terminal, how much power antenna is radiating is P rad is multiplied by in and the losses.
Okay.
Understood, right? It is just
Yes.
a ratio of other things, the losses. So that's why the gain and directivity also is also related as multiplied with ECD, the conductive and dielectric losses happening in the antenna itself. So now what happens? There are two particular definitions of gain, which is important or relevant. Okay. First one is called gain or IEEE gain. Why IEEE gain? Because IEEE standards define this gain. So that what happens now you come back to here. Here you see there are other kind of losses other than the conductive dielectric loss. What was the gamma loss or the losses due to reflection. So far in this concept, we did not take care of the losses due to reflection. Because IEEE standard says that the losses coming from impedance mismatch, which is reflection loss, and also polarization mismatch loss, that we'll also see here. So those things we don't take care here, okay, in IEEE gain. But it can also be taken care, then the gain will be further reduced, because all these things happen not exactly in antenna, but coming to the before antenna. See the reflection mismatch loss is happening in the junction of the antenna and the transmission line, right? That is not taken care, and also polarization mismatch loss that we will discuss later, also not included. So that's why it's called IEEE gain. And IEEE gain is defined in terms of this equation: G theta phi equals ECD into D theta phi. Is this understood, Binan?
Yes, sir.
Okay, so this is called IEEE gain. Next, we will see this is called realized gain. If you take all the other losses into account, then what gain we will have? Your gain will be further reduced, right? So this here it says it takes into account reflection loss or mismatch loss, and also the polarization mismatch losses. All other losses account taken into account. Here you have ER G theta D phi, so equals 1 minus gamma square into G theta G phi equals E naught into D theta D phi. So here if you see E naught is the total efficiency. Previously we are talking about only ECD portion. ECD is the conduction dielectric loss. But now if you take care of ER also, or reflection mismatch loss, here it will be given as E naught into D theta D phi. It is defined as realized gain. So in all the antenna terminologies, sometimes you will see realized gain, sometimes you will see IEEE gain. So now you know the difference. I hope you understood.
Yes.
Okay. Yeah. Is it clear, Nandana and Pavan?
Yes, sir.
Yes, sir.
Okay. Okay.
Sir, one doubt. IEEE and absolute gain both are same or different?
Sorry, IEEE and what?
Absolute gain.
Absolute gain, if you take there, you have to take further losses, like polarization loss, or there might be some other losses also. They will be all different. IEEE gain is IEEE gain only. There are no other terms for it. Generally, yeah. So generally, some of the papers or some of the books, they will talk about only gain, right? If they are saying about only gain, that means they are talking about IEEE gain only. Because in antenna and all these things, IEEE standard only we follow. Okay. If sometimes they specifically mention, then they will be talking about this realized gain. They will be saying realized gain is this, because the reflection losses will be happening.
Okay.
Okay. Yeah, so now our next topic of discussion is polarization. So as you know, polarization is everywhere. It is a very much important and necessary topic for discussion. Yeah. So do you guys have, did you study the polarization before? Do you have any idea that I want to know before starting?
Yes, sir.
Okay. And others, Nandana and Binay?
Yes, sir.
Okay.
Some basics.
Sir, yes, but it's bit confusing.
Okay, right. So now I will try to go into depth and clear the confusions. Okay. Do you understand this picture in the left hand side? As you know, there are two pictures, one upon the other one. So the bottom one, it shows the normal plane wave sine omega t kind of function, and the top it shows it is a function of space. So the wave, as well as if it shows the propagation in space, how it will propagate. And if you take a projection in a 2D plane, the bottom picture sin omega t will come. Are you understanding the top picture, the spiraling picture?
Yes, sir.
Yeah, so that is very vital to understand what polarization actually is. Others, Pavan and Nandana, do you understand the spiral picture?
Yes, there is a propagation.
So that is related to circular polarization.
No, not necessarily circular, any polarization, let's say.
Okay.
In elliptical also it may happen like that.
Okay.
Yeah, Pavan, what did you say?
Like he is showing a propagation of wave.
Yeah, propagation of wave, that is okay, but why it is spiraling like that? You got to see there are three axes, right? First
Yes,
one
sir.
is E, Y, E, X, and the third axis is omega t. Omega t is basically the propagation in direction, perpendicular direction, or wave propagation direction. And E, Y, and E, X is the electric field. If the wave has electric field in both Y and X axis, then what will happen? That it is showing. It is really plotting the electric field components, vector components, both EY and EX. And the bottom one you see, it is showing only EX, not the EY. Only it's showing the one component.
Yes, sir.
Yeah. So yeah, that means it has this spiraling picture has something to do with the two vector components of electric field, right? So you see, as the wave propagates from the left hand side to right hand side, so what happens? The electric field vectors. So if you have two components, the superposition or vector summation will be one component, right? Some component in the middle of EY and EX is the some vector summation. So that will be in some direction. Okay, let me mute for a second because some fumigation is going on. Yeah. So what happens? You see, there are multiple arrows pointing in the axis towards the curve. From the omega t axis, it has multiple arrows. So this is the field together. This is the vector sum of both UI and EX components. As you see, these arrows are like sometimes this side, sometimes that side, sometimes up and down, sometimes left and right. So that means what is happening in a particular, that means it is not constant. This direction is changing, right? So that direction means there is the combined direction of both Ui and Ex, electric fields Y and X component. So if you have two components, that means the vector component will be in particular direction. So that is not fixed. It is changing over time. That's why it is shown as omega t axis, right? And also now let's see, if you, instead of looking into whole omega t axis, if you look into one particular direction, one particular point at omega t axis, and you see a time lapse video, okay? That means as time changes, you fix your view in point O. You will see this angular arrow. It will keep changing over time. It will circulate over this direction, left, right, and all directions. That means over time, this electric field will keep changing over this whole circle. The arrow will be pointing sometimes this direction or that direction, like that. Okay. As the wave propagates through this point O in the axis, the electric field, direction of combined electric field, will keep changing. So this is only that, this is defined as polarization. What is polarization? Polarization is the direction of total electric field as it changes over time. Okay. So it says rotation of plane electromagnetic wave propagation in z direction. Okay. This omega t direction is, let's say, as z direction, perpendicular to both x and y. And the polarization is given as the rotation of the tip of this total electric field, or the direction of electromagnetic field. It keeps changing. This phenomenon is defined as polarization. And the right hand side, you see this elliptical thing, or it can be circular or any shape. Okay, that will come later. But for now, now you see this shape is what? It is at particular point in Z. You see, this Z is the omega t axis. Some point in omega t axis, if you take a cross section, and if you keep seeing that point over time, as we propagate over that point over time, you will have a elliptical circle, elliptical drawing like that. So that is given as the polarization ellipse at z equals 0 point as a function of time. Now, yeah, now you tell me what you did not understand or what are your doubts. Do you understand how this polarization ellipse is coming from the left hand picture?
So can you explain once more?
Yeah.
That right side figure?
Yeah. So left hand side, what it shows, it has three axes, right? EY, EX, and the third axis
Omega
is
t.
omega t or z. This omega t is the propagation of wave, is also the same as z direction. So now it says, instead of looking into all the z direction, you look into some particular point in z and see the wave as it traces the trace of this, the sum of the electric field vector, how it traces over time. If you look over a complete time, over complete circular time, right, the period of wave, how it rotates at some particular z, this will trace you this ellipse at z equals 0. Is it understood, or I should explain again?
Okay, sir.
Others, Pavan and Binay?
Yes, sir, I understood.
Okay.
Understood.
Okay. So now is that from the left side picture, we get the right side picture. Okay. And the vital or important part is we need to have two components. Okay. If we have two components, both EY and EX, we have a 2D plot. A circle or something like that, a 2D plot. Yes. But if we have only one component, what will be? It will be a line, right? It will not be a circle or ellipse. If we have both components, then only we have a circular ellipse. Or if we have only Ex or Ey, then we will have a line only. You understand? Because over that line, it will keep changing. So now we'll go to the next slide. So that means polarization is the electric field vector, combined electric field vector, how it changes over time at a certain or particular space in the wave propagation. If we look in a particular point in wave propagation, so there how the total combined electric field changes over time. That is defined as, is defined as polarization. It has to do with electric field vector. Yeah, now the most important factor is sense of rotation. How do you define this polarization? Okay, so there are many different terms here: clockwise, anti-clockwise, right hand, left hand. So now I will talk about this. How IEEE defines the rotation or polarization. So first thing is that IEEE says you have to look in the direction of propagation. Okay, so in the picture you see how it is defined. You have to look in the bottom picture. You see how the one eye is there. That eye sees in the arrow. This arrow is what? None other than z or omega t axis. Z or omega t is what? In the direction where wave is propagating. Understand? If you see like that, and from that direction, how do you see this the rotation over time? Is that previous curve in the right side curve what we have? We'll be talking about that curve, right side plot. Over time, how it happens, how it evolves, or how it changes over time. Now you see in this picture we see the person here. If he looks in the direction of propagation, he see that wave is propagating in the clockwise direction. Or also this clockwise direction can be with a hand it is defined as a right hand rule. Because right hand rule means if you point your thumb towards the direction of propagation, your other fingers give this kind of rotation, the rotation of field in the same direction. That's why it is called both as either clockwise or right hand. You can call this sense of rotation as clockwise polarization or right hand polarization. Is this understood? This you must know, because it creates a lot of confusion. You must understood that. If you once understand this, it will be very much clear.
Yes, sir.
Sir, can you please clockwise?
The clockwise thing you're saying. No, see, if you look in the direction of propagation, the picture shows what? It is going in this right hand side, right? Because your clock will also move in that direction only, right? From 12 o'clock, it will go to 6 o'clock and then again go back. It rotates in the same direction or not? That's why it's called clockwise.
Okay, sir.
No, is it clear? You see, that's why it shows a sign of clock also. Because the clock will exactly rotate in the same direction. I hope it's clear, right?
Yes.
Yeah, and the same thing is also if you point your right hand finger, thumb towards the direction, your other combined fingers will show in the same direction of rotation. You please try with your right hand now only, then you will understand. These are like actually difficult to show in in an online class, but you have to try it yourself. You take your right hand and maybe I will show my video. Let's see. Yeah, I hope. Can you see me? Yeah.
Yes, sir.
Yes, sir.
Yes.
Yeah. So now you see the thing is, where is the camera? Yeah. So you see, like this, you have to hold, right? Like this. This is my right hand, and if the wave is propagating from me towards the my iPad. So that is that finger pointing. The finger is pointing like that towards the camera. And the other things, my other fingers combined, it shows the rotation. From my hand, it goes in the direction of this. This direction, you see, this direction in again clockwise, right?
Yeah.
See, yeah. Is it understood? These fingers combined, it shows a clockwise direction,
Yes.
because the clock
Yes,
will
sir.
propagate like this. Yeah. Yeah. Bina, is it understood?
Yes, sir.
Okay. So that's why it's called right hand circular polarization. Okay, not circular. Circular will come later. It is called right hand polarization or clockwise polarization. So all this, it is, the reference is very vital. The reference is either you have to look in the direction of propagation, or your thumb has to, right hand thumb has to, point towards the direction of propagation. So yeah, you have to always remember that. The reference is same. If you take the opposite reference, it will be all different. You have to look in the direction of propagation or point your right thumb towards the direction of propagation. Okay, so that is okay. And the reverse is also there. Now they say, if you look in the direction of propagation and you see the wave is propagating in the other direction, the tip of the electric field is not in this direction, in the opposite, then it will be called counterclockwise. And also this counterclockwise will be called left hand polarization, because if there your right hand rule will not hold, then you have to hold your left hand and then so like that. You see the left hand and right hand, how beautifully it is completely different. The left hand, if I put like this towards the direction of propagation, it gives opposite counterclockwise direction, my other thumb fingers. This is my left hand and it shows like this. So the beautiful thing is, like, only our hands only can, give two separate directions, right and left hand. So all these things in, electromagnetics, you will have many times right hand rule, left hand rule. Why it is vital? Because two of our hands have completely different, directions. Here, if you see, is left hand is giving completely different sense of rotations. Yeah, I hope it is clear.
Yes, sir. Thank you.
Okay. Yeah. So it says, it says the sense of rotation is always determined by rotating the phase leading component towards the phase lagging component. Okay. So, and observing the field rotation as the wave is viewed as it travels away from the observer. So this away from the observer is same as, if you look in the direction of propagation, that means what? The wave is going away from you, right? That is what it says. So in Balani's book, it defines like that. The wave is going away from you. If you look in the direction of propagation, it is like that. And the rotation is also defined as, phase leading component towards the phase lagging component. That means if you have EY and EX, so both these are plotted, then only you will have this rotation, polarization ellipse. Now let's move to the other one. Okay, so now we have three different type of polarization. Okay, one is linear, another is elliptical, another is circular. So we'll see in what basis they are defined. Okay. So it says, the instantaneous field of plane wave, let's say it is some wave is traveling in minus z direction. How it will be defined? Is defined as EZT. That's the total electric field, given as EX is the X component and EY is the Y component, right? So that is how it is defined. So that means if we have a wave propagating in Z direction with having two components as X and Y, let's assume that. And based on that, we will try to understand whether it is linear or circular or other things. So how we can define the X component? X component, multiple times we know that a propagating wave can be defined as cos omega t plus kz plus phi x. So yeah, so now my question is, this is a basic question from basic electromagnetics. This why it is cos omega t plus kz. What do you understand from this? This term cos omega t plus kz plus phi x. What are the information do you have from this thing? From this term? So what is the direction of propagation of this wave? Can you understand from this term only cos omega t plus kz plus phi x?
Minus z.
It's a direction minus z.
Yeah, it's minus z, right?
Omega
That,
t is angular direction.
come again, Binay.
Angular direction. Omega t.
Omega t is angular frequency.
Yes,
That is-
frequency.
but omega t plus kz or omega t minus kz, that will only differentiate if the wave is propagating in plus z direction or minus z direction. You see, now we have assumed that wave was traveling in minus z direction. That's why it is defined as omega t plus kz. And phi x or phi y, you see, they have that means the two defined components, x component and y component of electric field, has two different phase, phi x and phi y. Their phase is different. That means at particular point in time, they are not in same phase. They have difference in phase. So from there only the polarization arises. Right? Now linear polarization is defined as the difference of this phase of these two components given by phi y subtracted phi x. Okay, phi y minus phi x. Is it understood how we are defining this phi y minus phi x?
Yes.
Yeah. So now linear polarization will say that when will it be linear polarization? When this difference in phase is given by n pi. Okay, it is n pi means you don't have only pi, then n will be 0, 1, 2 multiplies of pi. Okay, and that says E field vector possesses only one component. When will this n pi arise? So it describes those situations. If you have only one component, then it is okay. Obviously, you know the ellipse will now go to become a line, right? Understand? Because if you don't have ui and ex, obviously the sum cannot be in any other point. It will be only in a line, over a line. Then the difference will be only obviously n pi, because other component does not is not there always. And the other one says if these both components are there, two orthogonal linear components are in time phase or 180 degree out of phase. That means this phi y and phi x, they both of them exist, and their difference is either 0 or multiplies of pi. Then also it will be linear polarization. Even in this case condition, the wave will be what? It will be a line only. The polarization ellipse will become a line. Yeah, can you now visualize this? Is this definition clear when it becomes linear polarization?
Yes, sir.
Okay. Okay. So that means the difference between them has to be multiplies of pi. Okay. Now let's move to circular polarization. We will take the same electric x and y components and see in which conditions of phi x and phi y it will become circular polarization. So it says that magnitude of both these x and y components has to be same. Ex, you see, absolute value of Ex and Ey is same. That is Ex naught and Ey naught is same. And the difference between the phase is either 2n plus 1 by 2, that means it's a multiplies value of pi by 2. Some multiplied value of pi by 2, then only it will become a circular polarization. In some cases, it will be positive value of pi by 2, or some cases negative value of pi by 2. That will define it is clockwise or counterclockwise. So there are two sets of conditions to become circular polarization. First one is absolute value of E components are same, and the second component is they has to have a pi by 2 multiplies of pi by 2 as phase difference between two, pi difference of X and Y components. Okay, and the same thing is written here. The field must have two orthogonal linear components. That means EY and EX both has to be present. In case of linear polarization, even if only one component was present, it was happening. But here it will not happen. You have to have both EX and U components, Y components. And the second, it says the two components must have the same magnitude. Okay, that is clear that absolute values are same. And the third component says they must have odd multipliers of 90 degree. Now see, the odd multipliers, why is relevant? Because if you have even multipliers of pi by 2, that is same as multiply of pi only. Okay, even multipliers of pi by 2 means same as pi, and it becomes linear. Okay, yeah, do you understand this part?
Yes.
Okay, and the right side you see it's a analogy of DNA, strand of DNA. If you remember from biology, it looks kind of like this. So it has a similarity with a wave, that if a wave propagates like that, it will kind of be like a DNA, look like a DNA. So it says you can visualize the RF energy propagation from circular polarized antenna through space, just like that. So yeah, now the question here it comes, we are so far talking about only X and Y. But let's say the wave is not propagating in Z, wave is propagating in Y direction. So in propagation in Y direction, we will have electric field components maybe in EX and EZ. So now you must understand the same thing will be valid for any other components of electric field. Any two perpendicular combinations, be it EX, EY, EY, EZ, or EX, EZ, anything. So this condition has to be valid. Okay. But here you see the positive, this counterclockwise and clockwise has been defined in terms of plus and minus. But that I will advise you guys to not go by blindly from some equation, because they must have taken a reference z direction and all this that you don't see. So you have to have your own. If you have to given some wave, first you try to draw a elliptical polarization ellipse yourself. Okay, that's the first step. Given any particular wave, they will give you equation like this, cos omega t plus kz, and you have to draw your polarization ellipse. Okay. If you have that, from there you see how in which direction it is propagating, and also you see the direction of propagation. So you have, so these are three steps. First, draw the polarization ellipse. Second, you see the direction of propagation, and third is the rotation of ellipse. If you have these three things, from that you can determine the sense of rotation as well as clockwise, as well as linear or circular polarization, anything. It will be very easy. So first thing is you have to draw the ellipse. Okay, any question in this slide? No, right? Then I will go to next slide. Yeah.
Yes, sir, it's clear.
Okay. Yeah, so next slide is elliptical polarization. So, the circular and the linear polarization, both of them are the generalization of electrical polarization. Electrical polarization is the most general form. If you have some conditions imposed on this, then it becomes circular or linear. Okay. Now you see what it says. So elliptical polarization is also, we have taken the same set of equations, Ex and Ey components. So in what conditions we will say? See, it is if the absolute values of fields are not same, Ex not equals Ey not. And the difference between the phase, it is, it can be anything. It actually, when it can be multiplies of pi and all, multiplies of pi by 2, even and odd. Okay. But the electric field values are not same. Absolute values of them are same, not same. So here it says the field must have two orthogonal linear components as usual, and the two components can be of the same or different magnitude. Okay. So it can be same or different magnitudes. Yeah, Binay?
Same or different magnitudes, sir? Ex and Ey.
Yeah. I'm coming there. Yeah. So this, the confusion is the same and different. So let's take the defined magnitude. So this is very much, I suppose, clear. If the Ex and Ex naught is not equals Ui naught, then it is elliptical, no doubt. But now it says when it is same component. Let's say Ex equals Ui. Absolute value of them are equal. But when still they will become elliptical polarization, when the phase difference is not a multiplier of pi by 2. It is any value, let's say pi by 6, pi by 7 or something. There it does not matter. The electric field value is, the absolute values are same or different. In that case, it will obviously be elliptical polarization. Do you understand that? Vinay, is it clear?
Sir, Ex and Ey both are in same magnitude, but
Yeah. But now see, now what happens? For circular polarization, you need to have a odd multiplier of pi by 2, right? But that does not happen. If that does not also happen, it's not a multiplier of pi by 2 at all. It is any value of pi, pi by 6, pi by 8, pi by 7. So even though they are same, it does not become neither circular, neither linear. Then what will you call it? It will be called elliptical polarization.
yes, sir. Now I get it.
Understood, right? And the other case is very easy. Even though you have, if they are not same at all, Ex equals not equals Uy, then obviously it will be elliptical. There are no doubt on this. Yeah, Nandana and Pavan, do you understand this?
Yes, sir. Actually, from elliptical polarization, circular polarization is actually a subband of elliptical. Is that
You can say it's a generalized form. Yeah.
Yeah, okay. So from elliptical only, different configurations can be obtained.
It can be obtained, but
Uh,
sometimes also people prefer not to mix everything together. So you take elliptical as separate only. Yeah.
Okay.
Yeah, you take it as separate. Linear, circular, and elliptical, you take as separate only,
Separate.
not to confuse. Yeah.
Okay.
Yeah, so now all this polarization concept was defined in terms of what? In terms of any electromagnetic wave. Okay, this is same for if you take X-ray, or you go to photonic range, or light, or any other electromagnetic wave, it will hold. That was same for everyone. Now we have to come to our antenna. Okay, you have to see what will be polarization of our antenna. That's why, because we are studying antenna theory, right? So now we see what it says. So again, we are considering the sphere. Okay, in the center of the sphere, we have our antenna. it shows in antenna location at the center. So now how will you define the polarization of an antenna? So it says polarization of an antenna is given or directed. These are IEEE definition. Okay. So it is defined as the polarization of the wave transmitted by the antenna. As you have seen before, polarization was defined for what? For a particular wave. For a particular wave which was transmitting in some direction and all this. But how do you connect with the antenna? Now IEEE says it has to be defined as the wave polarization of the wave transmitted by the antenna. So here, that's why in the sphere you see the arrow points outward to the sphere from the antenna location at the center. And yet the boundary or the outer layer of sphere, if you take some point, which is, let's say, the outer layer of the sphere is the far field. Okay. So at some point in the far field or on the sphere, what would be the polarization in that point? That would be the polarization of the antenna. Is this portion clear? Because here it says just below the picture is written direction of propagation here is in radial direction from the transmit antenna. Antenna is in the center of sphere. I hope you understand this thing. Is it clear?
Yes, sir.
Okay. So now see next come to the next points. Note when the direction is not stated, says when the direction is not explicitly stated, then the polarization is taken to be the direction of maximum gain. Okay. Now it in the far field it can be many other directions. So we will take the direction of the polarization as the direction of maximum gain. Yeah. Now see the directivity gain in all these things, even polarization, all these things, we generally refer it to the direction of maximum gain of antenna. That's why you need to know the radiation pattern of antenna and find out what is the direction of maximum gain. From that you can find all these different terminologies. Okay, so this is one part. The next part is says polarization of the wave received by antenna. But it can also be, now you see, in this case, we are saying the antenna as a transmitter. Okay, the wave was coming from the antenna outward. Now it can be also true that antenna is acting as a receiver. So wave will be coming in the inward direction of the sphere, not the outward. Okay. So in that case, the polarization of the plane wave incident from a given direction and having a given power flux density, so which results in the maximum available power in the antenna terminals. So it's defined like that. So yeah, now I will tell that this definition is not so much important, but what the actual practical implication is that it is defined in the transmitting mode. Even for a receiving antenna, polarization will be defined as the transmitting mode. IEEE definition says that even for a receiving antenna, you see what would be the polarization for the transmitting mode of the antenna. The same antenna, same polarization is taken as the receiving antenna polarization also. So even for the receiver antenna, we define in terms of transmitting mode. That is what IEEE says.
Sir, is there any reason for that or just for a better understanding?
This is definition of IEEE. Yeah, because see why IEEE defined all these things, because there are so much confusions, right? To remove all this, to clarify things, these are the IEEE definitions. Okay. Because if sometimes we will be having antenna as radiator, sometimes as transmitter or receiver, so that will mix a lot of things and create confusion. So IEEE defined that you always look it in any antenna has the transmitting mode. In the transmitting mode, what would be the direction and the sense of polarization? All these things you use in the same case. May it be transmitter, may it be receiver. Yeah, I hope that was clear. Now the next vital concept is called copolarization and cross-polarization. So in all the antenna theory or any paper or anything, any book, you will see this is a very important concept. So many a times the radiation pattern will be defined like this. In the bottom you see, it will have two plots in same figure. Copolarization, cross-polarization. The red curve is given as copole or copolarization and the blue dotted lines are cross-polarization. So what are the differences between them? And why it is important to define it like that? So it says the antenna is never 100% polarized in a single mode. So see, we have multiple modes like linear, circular, and elliptical like that. So generally in the antenna, it will not be a pure, pure mode is excited. So it will create some amount of linear polarization, some amount of circular, and all this. So how do you measure that? How good is your antenna? So that's why these terms have come into picture. So it says, hence, the radiation pattern of an antenna is usually resolved into a pair of orthogonal polarizations. So these two orthogonal polarizations are defined as copolarization and cross-polarization. Further it says, copolarization is polarization the antenna is intended to radiate. Why it is co is actually we want our antenna to radiate this kind of polarization. But because of some kind of error or some kind of fabrication problem or anything, there will be some opposite orthogonal polarization also. That is defined as cross polarization. Understand? So now in the right side picture you see the actually what we wanted is the black or vertical polarization, desired polarization. But because of some problem, we are also getting a horizontal polarization. That is the orthogonal mode. So the black vertical side line will be our copolarization, and the red line will be our cross polarization. Similarly, in the bottom one, you see the desired polarization is black one, the left hand circular polarization LHCP. But due to some other problems, we have a right hand circular also. That will be called cross polarization. Yeah, so is this part clear?
Sir, in bottom right hand side, these both are showing right hand or left, right hand or no?
Yeah. That you have spotted right. The direct sense of direction is same, but it is just for the visualization. It does not actually show. Yeah.
Okay.
Yeah. So it's saying it should be opposite, the orthogonal mode. That is what it means actually. Yeah. So now the practical part is how do we do in the antenna actually? In antenna measurement. Did any one of you do any antenna measurement in fabricated and measured antenna pattern, radiation pattern?
No, sir.
Okay, you did. So, yeah, can you tell that how do you measure actually this co-pole and cross polarization? Yeah, generally you tell me like, yeah, what do you measure in antenna pattern, radiation pattern?
I said no, sir. No,
Sorry.
I did.
Okay, no.
Yeah.
Yeah, okay, yeah. So now let's see. So in a practical measurement, what we do is that we take two planes, okay? One is E plane, another is H plane. That is what we measure. So what happens that Maybe I will switch on my video once again and see. So let's see, these are two. Okay, these are the two antennas. Let's say. Okay, so why two antennas? So this one, and in our measurement setup, we will have this one antenna always fixed. This is our reference antenna. Okay, this reference antenna will act as a transmitter. Generally, what we do, we keep a fixed transmitting antenna. That is our reference antenna, which we know the gain and radiation pattern on all this. This is fixed. Okay, that we have always in our anechoic chamber fixed. Now let's say you have fabricated one antenna. This is your another antenna you have fabricated, and you have to measure the radiation pattern and polarization on all these things, gain, directivity. What will you do? This is our reference antenna, reference transmitting antenna, and this antenna generally we connect to the receiver. Okay, this our fabricated antenna. This hand, this my right hand is the fabricated antenna we use. So both of them are kept like that. So now you see, let's say both of these antennas we have to measure. So what do we do? This our fabricated antenna we rotate. We rotate this antenna in one plane like this, 360 degree, and take we measure the received value, S parameters. Okay, and also then we have also move the antenna like this, and then also we rotate. So why we do like that? Because for antenna like this, we will have two planes. We have to take E plane and H plane. So what would be E plane? E plane will be like this, and H plane will be like this. For our antenna, our test antenna, we have these two planes. We have to measure in this plane, E plane, and this H plane. Okay, so this you please try to understand, because these are the practical aspects you will not find anywhere. So I'm telling, see, you have to measure in two planes, E and H, E plane, H plane. This is your reference antenna. And what do we actually measure? We measure the S parameters only, right? So S parameters will give you the received power, received power and transmitted power. From that, we calculate all these things here in the, in this slide you have seen, the people they have drawn. These are all from the S parameters only. So now how do we do this, how this copolarization and cross polarization comes. This is our antenna, reference antenna, which is always fixed. And this is our actual test antenna, what we have fabricated. So what do we do? Once we know the E plane and H plane, okay. Let's say this is both the transmit antenna or reference antenna, E plane is this, and our test antenna, E plane is this. We align them both. And then we rotate the antenna like this, 360 degree. So this will give you the plane, the electric field pattern of, or the radiation pattern of E copolarization. Okay, E copolarization will be given through this. Now if you move the antenna to the perpendicular like this in the H plane, but your reference antenna is same, then you will get now you will get E cross polarization. Now if you move the antenna like this in a horizontal plane, you will get, because your test antenna is in the H plane, but your reference antenna is always same in the E plane. That's why it will be called as E cross, eco and E cross. Is this clear?
Yes, sir.
Okay. So this is two. This is
Sir,
yeah.
Like the method you taught us, like rotating in azimuthal and elevation and directions. It is same for calculation of antenna radiation pattern of the receiver antenna, right?
I did not understand. You refer to what?
Like you are transmitting power from the reference antenna. You are radiating the power. Like if you don't know the radiation characteristics of the receiver antenna. Is this the same test you will be using for determining the pattern of the antenna, receiver antenna?
You mean you don't know your fabricated antenna, how it will perform?
Like after fabrication, how much gain it is?
Yeah, that is what you are supposed to measure, right? We are talking about the measurement of your fabricated antenna.
Yes.
Then what? I did not understand your question clearly.
Like both are same experiments, like for co-polarization and cross-polarization
No.
measure.
Both the same means what same?
Setup is same, right? Like how we are.
Antenna setup is same. Only you have to rotate the antenna. That's all.
We are rotating the receiver antenna.
Receiver antenna, but in the other case also it has to be rotated. Now we are talking about only E plane. That's why I said na, E co and E cross. Right? The next will come H co and H cross. There, both the antenna has to be rotated like this.
Okay.
Our reference antenna will be in the H plane as well as our transmit antenna. When this happens, this pattern, if you measure like this, is called H co-polarization. Now, if you keep your reference antenna same and move your transmit antenna to other plane, E plane, this will be called H cross polarization. This will be H co and this will be H cross. So now you see all is reference to your reference antenna. Your reference antenna has to be placed in some plane. From that now you understand what is happening. So total generally we take 4 measurement: E co, E cross, H co, H cross.
Okay, sir. Understood.
Yeah, other people, Nandana and Bina, do you understand?
Yes, sir.
Yes, sir.
Okay. So yeah.
So actually polarization is the basic for this co and cross, which means co is actually the intended or the receiver antenna's polarization, and cross is what?
Yeah, what you don't want. Yeah.
Okay. Okay, sir.
Yeah. So in ideal situation, when you place both of this should be maximum, and if you place like opposite direction, it should be 0. But it actually does not happen. There are some stray polarization fields that will be still 0. Because that's why here in the plot, if you see, there's so much difference in magnitude between the red and blue plots, right? So it in ideal condition, it was supposed to be almost 0, but it actually does not happen. So we have to measure like this. Yeah, both in same eco and both is in double. It should be H polarization. So most of the papers, research papers you study, they will define it like that: eco, E cross, H co, H cross. So yeah, so they fabricate their antenna and measure it like that. Okay. Yeah. So now there is concept of polarization loss factor. If your two antennas, transmit and receive antenna, does not match in polarization, there will be some loss happening, obviously, right? If they are not properly aligned, there will be polarization difference. So this is defined in terms of polarization mismatch. So in the picture you see, there are 3 pictures. So where this dotted line and the solid line both aligned. So there the polarization loss is 1. PLF is 1. Loss factor is 1 means loss is 0 actually. It is defined in opposite terms. And then separately it is defined in terms of rho omega dot product of rho A. What is rho omega dot rho A? These are the unit polarization vectors. So difference between them will give you the cos omega p square, which is the angle of polarization. Difference between polarization angle difference between transmit and receive angle, receive antennas. So from that, it will cause some kind of polarization mismatch. If they are both aligned, then it will be polarization loss factor will be 0. You see, it will be 1. It will be 1. And in the rightmost picture, you see, both are perpendicular. So there the polarization loss factor is 0. That means there will be complete mismatch. So no wave will be actually received in the other side from the transmitted antenna. So yeah, I highly recommend you go to Balani's book and this portion you look into one or two examples in polarization. Then only it will be clear. You do one or two examples, and if you have any problem, then you can come to next week. Tutorial session. I can explain if you have any doubt. Okay. So this Balani's book you have, I don't know, it is available in internet also. Um, you please look into. There are many examples solved out and very clearly explained. If you don't do one or two math, it will not be clear. Okay. So okay, then we will continue on this on tomorrow from this portion, input impedance and all. So today we'll end it here. So yeah,
Okay.
any doubt, please clarify. Ask me tomorrow.
Okay.
Bye. Thank you.
Okay, sir. Thank you.
Thank you.